Number one, the drag force Ft acting on an object falling through air is given by this equation, where A is the cross-sectional area of the object, B is the velocity of the object in the air, rho is the density of the air, and C is the constant. C is constant called the drag coefficient. Okay. Use SI base units to show that the drag coefficient has no unit. So we are going to prove that C without units. Okay. Based on this formula, FD half C multiply rho multiply A multiply V squared, because V squared through this velocity. So velocity squared. Okay, based on this information that FD, okay, FD, the unit is kilogram, meter second, power minus 2. Rho, density unit is kilogram, meter power minus 3, okay, kilogram per meter cube. And then A, area, it means meter square. Then V, velocity, is meter per second. So if V meter per second, it means V squared. V squared equals meter, meter squared per second squared. Okay. So from this units, we're going to find C, FD half times C, this formula, rho A and V squared. Substitute this units, half C, because C without unit, and then rho kilogram per meter cube times A meter squared, okay, times, and then this one, V squared, meter squared over second squared, okay, and this is FD is kilogram, meter per second squared, okay. It means half C becomes kilogram meter per second squared over this unit, kilogram per meter cube times meter squared second per meter squared, and it will be kilogram meter per second squared over kilogram meter per second squared. Okay, because this meter, this one to meter becomes like this. Okay, so it is half C equals 1, or C equals 2. Constant number without units. This. Okay, what else? I think this is clear. Okay. Yeah. Meter becomes meter because This is power minus 3, and this is power 4. Next, figure 1.1 figure 1.1 shows a sphere falling at terminal velocity in air. Assume that the upthrust on the sphere is negligible. On figure 1.1, draw and label arrows to show the directions of the two forces acting on sphere. So there are two forces acting on its sphere, and uh, two forces are uh, the first one to downwards, that is weight, okay, mass times gravitational force, and to upwards is FD. FD uh, is the force to upwards. Yeah. Because now this based on this info that FD, okay, uh, drag force, yeah, acting on the object falling. So, and the direction of this force is to upwards. Assume that the already here, see the mass of the sphere is 49 grams. Calculate the drag force. Okay. So, okay, the drag force equals m times g. Okay, to this the and it becomes 0.049 because this is grams. Okay, you have to convert becomes kilogram. 49 over 1000 is 0.049 kg. Okay, and multiply by 9.81. This is gravitational force, and the result 0.48 Newton. Okay, so here 0.48 Newton. The sphere is falling in air at terminal velocity of 25 in SI base units. The density of the air is 1.2 in SI base units. The diameter of the sphere is 0.060 in SI base units. Use your answer in C to calculate the drop coefficient C, okay, for the sphere. Okay. Given that FD equals a 0.84, okay, newtons, rho 1.2 kilogram meter per meter cube, and D equals 0.060, okay, right? So it means radius half of uh, the half of diameter. So it becomes 0.03, half of diameter. So diameter divided by 2. And area is pi r squared because this is the sphere. So the area is a circle area. And then it is pi times 0.03 squared. It is 0.0009 pi. Meanwhile, for phi squared, okay, 25 squared meter squared per second squared. Okay. So velocity 25, this is phi, okay, phi 25 meter per second. So if phi squared, it means becomes 12. And next, it means FD, half C times rho times A phi squared. Half uh, half C times this one, 1.2 kilogram per meter cube times 0.0009 pi times 25 squared meter squared per second squared. Okay, and 0.48 Newton FD. This one. So 0.48 Newton, and if you calculate, becomes 0.3375 pi C, and the unit kilogram over meter second squared. And then after that, yeah, pi, this is Newton, okay? Kilogram per meter second squared, this is Newton. So we can write in 0.3375 pi Newton. Okay, C here, this C. So we can calculate C to 0.48 Newton over 0.3375 pi Newton. Okay, and the result is 0.453. Of course, you have to convert pi into 3.14 or 22 over 7. And you can get this result. Number 2, define velocity. Okay. Velocity is change in displacement. Okay, so in velocity, uh, you can calculate through displacement. Okay, displacement over time. So when you push something and it not move, it means there is no velocity. So you can calculate the velocity if the object moves from the initial point to the final point. Okay, so that's velocity change in displacement. A student throws a ball over a vertical wall of height h is shown in this figure 2.1, this figure. Okay, The ball leaves the hand of the students at height 1.2 meters, okay, above the horizontal ground. This is the horizontal ground. The ball has an initial velocity 22 meters per second at an angle 40 degrees to the horizontal. This the angle, okay, between uh, the horizontal strike line and the path of this ball. The wall is a horizontal distance of 36 meters. So from this initial point to this point, okay, uh, 36 meters, okay, from where the students release the ball. A distance is negligible, or it means uh, not including a resistance. Determine the time taken for the ball to reach the wall. Okay, so we are going to calculate uh, how long from this initial point till here. Okay, okay. Uh, so the horizontal velocity we have to calculate horizontal velocity. Okay, uh, equals 20 times cosine 40 cosine 40 because the angle is 40. So if you calculate, you can find the result 16.85. Okay. And after that time taken, based on this request, time taken equals d over v. Okay. And this is the velocity, this one. Then this is meter per second. And distance is 36 meters over 16.85 meter per second. And if you calculate, you can find the result 2.1 seconds. So this is 2.1 seconds. To calculate the vertical component u of the initial velocity of the ball. Okay, so for component u or initial velocity, okay, when the students throw the ball, okay, uh, the formula of initial velocity is 22 times sine 40. Okay. Uh, just now cosine, but this is sine. So the initial velocity equals 14 meter per second. So this is 14. Okay. And part three, the ball just goes over the wall. Okay. Over the wall, it means through this wall. Okay. Already passed, already over the wall. So the question is calculate the height of the wall. Okay. I'm going to, you can use displacement formula that S equals ut, initial velocity times time, plus half at squared. And it is the initial velocity 14, 14 times 2.1 plus half times acceleration 9.8 then times 2.1 squared. And if you calculate, you can find the result 7.8 meters. So height of the wall is 7.8 plus 1.2 meters. So it becomes 9 meters. This is 9. Number 3, state the principle of conservation of momentum. I'm going to change my pen in. Okay. So the principle of uh, conservation of momentum uh, says that total momentum before collision is equal of total momentum after collision. Okay, or we can say that total momentum, total momentum of a system is always constant. So why? Because before collisions and after collision, the total momentum is same. Okay, is equal. So that's why we can say that the total momentum of a system is always constant. An object of mass 2m is traveling at a speed of 5 meters per second in a straight line. Okay. This object. It collides with an object of mass 3m, which is initially stationary as shown in figure 3.1. Okay, so this object moved to the right, okay, and will be collided with this object, this object 2m, while this one object 3m, and with velocity of 5 meters per second, and between this object and this object, the distance, if this is 5, is 5 and 5, so it means 10 meters. Okay. After the collision, after the collision, the object of mass 2m moves with velocity v, okay, at an angle 30 degrees to its original direction of motion. Okay, so after when collisions, it moves uh, to upright to here, okay, with uh, angle 30. As well, the object of mass 3m, okay, move to downward with velocity w, f2m, velocity v. Okay. Also at an angle 30, as shown in figure 3.2. Right. By considering the conservation of momentum in 2 dimensions, calculate the magnitudes of v and w. So we're going to calculate the velocity of this object to m and the velocity of this object. So it means based on this question, we will calculate v and w. Okay. Motion, I will start with motions along the direction, okay, the strike direction. Uh, the momentum will be 2m times v. This is the velocity of 2m, okay, plus 3m w is velocity of 3m. Okay, sorry, with cosine. Okay, cosine 30 because the angle is 30. Okay, cosine 30 plus 3m w cosine 30, it equals 10 meters. Okay, and 2m v cosine 30 is square root 3 half plus 3mw square root 3 half, 10 meters. I will calculate with 2 over square root 3. So it will be 2m v plus 3m w equals 20 over square root 3 meters. Okay, and becomes, I will find first in this, I will divide this area, this motion along direction, and we're going to calculate motion perpendicular. Perpendicular to direction. Okay, so it means the angle is perpendicular. If perpendicular, it means they call that perpendicular. It means 90. Okay, so this angle is 60 as well. This angle is 60. Okay, so 2m v cosine 60 is equal 3m w cosine 60. Okay, and yeah, right? It comes to mv plus 3mw. So m, right? So v equals 3 half w. So substitute into this equation becomes 2m times 3 half w plus 3m w 20 over 3m. Okay, so it becomes m, I cancel, and then it's gonna be 6 because 2, this is 2 divided by 2 equals 1, 3 plus 3 equals 6. 6w equals 20 over square root 3. And w equals 20 over 6 square root 3. W equals, I will calculate first, it is 1.9 meter per second. And how about V? V equals the half times 1.9. It is 2.9 meter per second. So, okay. So V equals 2.9 meter per second, while W equals 1.9 meters per second. See, an object of mass 4.2 kg is traveling in a straight line at a speed of 6 meters per second. The object is brought to rest in a distance of 0.05 meter by a constant force. Calculate the magnitude of this force. Right. The first step we need to, if magnitude of this force, we need to find the work done through this formula, kinetic energy, because this object moves, so we need to calculate the kinetic energy. Kinetic energy happening on an object move. Okay. So the formula is half m v squared. It is half times 4.2 because this is 4.2 kg times 6 squared. If you calculate, will be 76 joule. And force equals work done over distance. Work done is this one, 76 joule over distance, one 0.05 meters. So it is 1,500 Newton. Number 4, define strain, okay, or understanding of strain, right? Uh, for me, strain is a comparison, or I would like to using term the ratio. Okay, so strain is the ratio of change in dimension of a body dimension of a body due to or because of stress to original dimension. Okay, so strain is the ratio of change in dimensions of a body due to stress to original dimension. Next, B, a copper wire of length 4 meters has a uniform cross-sectional area of 4.5 times 10 power minus 7 meters squared. A tensile force of 18 Newton is applied to the wire. This causes the wire to extend by 1.4 millimeters up to its limit of proportionality. Calculate the Young modulus of the wire. Right. I would like to calculate stress first because we can calculate Young modulus through stress over strain, right? So stress equals 18, okay, 18 Newton over, is it 18 Newton over, sorry, not this one, this one, I mean this one, area, okay, not area. So 18 over 4.5 times 10 power minus 7. And it is 18 over 4.5 times 10 power positive 7. Okay. Or if you calculate, the result will be 4.0 times 10 power 7. Next, strain. Strain equals this 1.4 millimeters. Convert to meters. So 1.4 over 1,000 over 4. uh, Because we have to convert into meters like this one, this unit. So it will be 1.4 over 4 times 10 power minus 3 because of 1,000. So if you divide, uh, finally you can find this result 3.5 times 10 power minus 4. Supposed to be this is 0.35, but I already convert into 3.5 times 10 power minus 4. And young modulus we can calculate through uh, through stress over strain. Okay, and it is 4 times 10 power 7 over 3.5 times 10 power minus 4. So 4 over 3.5 times 10 power 11. And it is 1.1 times 10 power 11 Pascal. Okay. So this is 1.1 times 10 power 11. Next, what else? Part 2. On figure 4.1, draw a line to show how the stress varies with the strain for the wire up to its the limit of proportionality. Okay. Now look, the axis. This is the axis of stress for the vertically axis, and this is the axis for strain, the horizontally axis. So look that if we look strain how much and stress how stress is 4 times 10 power 7, while strain 3.5 times 10 power minus 4. Okay, this is stress 10 power 7. It means 4 times stress is 4 times 10 power 7, while strain is 3.5 times 10 power minus 4, 3.5. It means here I'm going to between the different color. Okay, this is 3.5. Okay. And after that, 4 here. So the coordinate point, yeah, this one is the coordinate point. Coordinate point of 3.5 times 10 power minus 4 and 4 times 10 power 7. This the coordinate point. Okay, and then we're going to create a straight line from origin to this coordinate point. Okay. Okay. That is the straight line or the graph, uh, the straight line about this. The stress fire varies. And see, a second copper wire has the same length, okay, as the wire in B, but a larger in diameter. Larger in diameter, both wires are subjected to a tensile force of 18 newtons. Okay, it means less than the previous one. Okay. Okay. Oh, uh, same, the tensile force 18 Newton, but the difference is here. The diameter. Okay. Uh, Diameter of the wire. Okay. If diameter of the wire larger than the previous wire, so implicated to the stress and strain. Okay, both wires are subjected to a tensile force of 80 newtons. Okay. By placing a tick in each row, complete table 4.1 to compare the stress and strain of the two wires. Of course, if the wire diameter larger than the previous one, uh, the stress will be less in second wire. It not greater, but less as well. Strain will be less in second wire. Number five, a stretch string PQ has length 1.2 meters. One end of the string is attached to a vibration generator, this, and the other end is attached to a wall, this. So P and a vibration generator while Q at the wall. The vibration generator is switched on and a stationary wave is formed on the string. The string is shown at one instant of time in figure 5.2. So being this, okay, when the vibration happening, this string, wait, this string will be like this, has 1.5 waves. Okay. Explain how a stationary wave is formed between the vibration generator and the wall. Okay. Uh, the waveform, because due to vibration of a generator, and after that travel. Okay, the the wave travel along the string. Okay, along the string and reflect. Okay, and reflected at point key. Okay, so look, so this is the condition that when when this generator switches on, the wave happening, and then uh, the wave will form, the wave form on the string and then reflected on point Q. Okay. This is the wall. Calculate the wavelength of the stationary wave shown in figure 5.2. Okay. Uh, this wave, one wave from this point into this. So one wave. So it means this is 1.5 wave. So 1.5 wave. Look, I'm going to the string is the string length is 1.2 meters, and one wave one wave consists of a crest and a trough. A crest and a trough. Upward is a crest and a trough downward. Two two crest and one trough. So it means one, two, three. Okay, so if 1.2, if 1.2, it means this is 1.2 divided by 3. So it is 0.4, as well as this is 0.4. The distance, this is 0.4. Okay, so the wavelength of the stationary sound is the wavelength is the wavelength. Okay, there's a straight line here. Okay, this is 0.4 and then 0.4. So the wavelength equals 0.8 meters. 0.8 because 0.4 plus 0.4. Figure 5.3 shows the stationary wave at time t equals 0 when all points on the wave are at their maximum displacement. Okay. The period of the wave is 0.16 seconds. On figure 5.3, sketch the shape of the stationary wave at time 0.25 second. Right. If time 0.25 second, we can determine the period of the wave. The period of the wave formula is T over N. Okay. T is 0.24, while N equals 1.5. Just now I told you that this wave is 1.5 wave. One wave consists of one crest and one trough. Okay, so there are two crests and one trough, so it means 1.5. Better if I write here trough. Okay, this is crest. So 1.5, 1.5 wavelength. Okay, so 0.25 divided by 1.5, and it is 0.16. If 0.16 second, it means uh, I will sketch with the same. Okay, I'm going to use in this one. Okay, if 1.6, it means same with uh this wave. So same, so sketch like this. Okay, because they have the same. Yeah, that's one. Same wave. Even if the time 0.16, uh, we'll have the same wave if the time 0.25 second. Okay. Points R and T on the string are horizontal distance of 0.3 meters apart and in the positions shown in figure 5.4. Question. State the phase difference between the oscillations of points R and T. Okay. Uh, Positions of R and T look that actually they are in a straight line. one another. Okay. If straight line, it means uh, the phase difference is 180 degrees because their positions on a straight line. Calculate the speed of the progressive waves on the straight string. Okay, so speed or velocity equals lambda over t over a period. Lambda equals, if I'm not mistaken, just now 0.8. We already 0.8. Wait, what I said was this one, yeah, the wavelength. Okay, so 0.8 over I'm gonna check 0.16. Yep, this one 0.16. And if you divide, it is wait 6. Yeah, 5 meter per second. So listen here, speed equals 5 meter per second. And number 6, state Kirchhoff's first law. Okay, Kirchhoff's first law says that the sum of electricity current which flowing into the junction is equal this these are the keywords is equal within the sum of electricity currents flowing out. Okay, flowing out. Okay, so into equal out of the junction. A cell with internal resistance R is connected to two resistors of resistances R1 and R2 as shown in figure 6.1. So there are two resistors, this R1 and R2, attached on the circuit. Potential differences across R1 and R2 are V1 and V2. So there is V1 and V2, okay, respectively. The terminal potential difference across the cell is V. So this is V here. The current in the circuit is I. Okay, this one. Use Kirchhoff's laws to show that the total resistance RT, this is total resistance of the external circuit is given by RT equals R1 plus R2. Okay. Um, I would like to start with phi. Okay. Potential difference equals electricity current times resistance. Okay. So total potential difference equals V1 plus V2. Okay. Or it is IRT, okay, current times resistance, total resistance equals current times R1, R2. After that, I will divide by I, and it becomes RT equals R1 plus R2. This. Next, the electromotive force EMF of the cell is 1.5 volts. The values of R1 and R2 are 10 ohms and 15 ohms respectively. The terminal potential difference of the cell is 1.35 volt. Okay, so the electromotive force 1.5, while the potential difference of the cell is 1.35. Calculate the internal resistance. We're going to calculate the internal resistance of R of the cell. So I equals V over R1 plus R2 because R1 and R2 attached on series. So on series circuit, not parallel. So it means 1.5 over 10 plus 15. And if you calculate 1.5 over 25, it is 0.06 amps. Okay. And this is electricity current, I, electricity current. And now we're going to calculate R, or the internal resistance, equals uh, electromotive force minus the terminal potential difference over this electricity current. So it is 1.5 minus 1.35 over this result, 0.06. And if you calculate, it will be 0.15 over 0.06 ohms. And the result is 2.5 ohms. You can calculate based on your calculations. Maybe if I have mistaken, but I got 2.5 on my calculator. A resistor of resistance R3 is added to circuit figure 6.1. So which one? The added R3. Okay, the third resistor. So that the circuit is as shown in figure 6.2. Okay, so the previous circuit just have R1 and R2 attached on series circuit, but what R3 attached on parallel circuit. Okay. State and explain the effect, if any, of this change on the current in the cell. So what happened if added one more resistor becomes like this and attached on parallel? If parallel, it means the electricity current will be increased. Okay. So the electricity current will increase. Why? Because it will, total electricity current will be I1 plus I2 plus I3. Okay. How about resistance? Different if resistance will be 1 over R equals 1 over R3 plus 1 over R1 plus R2 because it's parallel between R1 and R2 and R3. So the current will increase while resistance decrease. Okay, because the third resistor is parallel. The terminal potential difference. So what happened with the potential difference of the cell? So as you know that the formula is V equals I times R. Right. So the implication potential difference here will be increased, and this one will be increased as well. So implication for the potential difference at the terminal would be decrease. So the potential difference will decrease at the terminal. Number 7. Nuclei of an isotope of copper each have 29 protons and 37 neutrons. This isotope is beta minus beta negative emitter. State the nucleate notation in the form, and this form. Uh, this is isotope, okay, for this nucleus of copper. Okay, copper has 29 protons and 37 neutrons. It means if you copper forces one Cu and then 29 here, 29 plus 37, 66 here. Okay, that's well. And the energy spectrum of the beta negative radiation emitted by a sample of this isotope is shown in figure 7.1. Use figure 7.1 to explain why other particles apart from the beta negative particles must be emitted during this decay. Yeah, correct. Because if you look this graph, uh, why happen the other particles apart from beta negative? Because the energy of decay is constant. Okay, so look at this graph, but the energy decay, more and more decay, and so on. Okay, so I'm going to writing due to the energy of decay is constant. Okay, state the name of the other particle emitted during the decay of of this isotope, of course, electron. And what else? Part three, the copper isotope decay to an isotope of zinc. Right. Give the radioactive decay equation for this decay. Include the nucleon and proton numbers of all the particles involved. Okay. So there's now copper. If I'm mistaken, it's 29 and 66 here because 29 plus 37. So if zinc, okay, that means 66, 30 here. Okay, so it means beta particle zero here because already 66, 66. It's been minus one here. Okay, because it's 30 and this is 29, so it should be 29. And it means without other extra particles. So zero, zero. Okay, so then thank you for joining with me in this lesson. If you have any questions, you may email me. And if you have different calculations, you can uh, inform me as well through my email. Thank you for joining with me. Bye.